Hello and welcome. Today I will be presenting our work on an interactive visualization for neuronal network simulations of plasticity changes in the human brain. First, I'd like to give an overview over our thought process and motivations for designing our workflow. We wanted to have an application which would allow the user to interact with the data in real time and at the same time be very flexible in its applications. To achieve this, we developed an application using the Unity game engine and allow the user to enter in expression using the different attributes of the simulation and show it in real time for all neurons. And at the same time, we also render the connections as they are made and dissolved by the model. The dataset includes 4 ensembles, and each ensemble includes 10,000 captured frames for 50,000 neurons with 12 attributes for each neuron. This is quite a volume of data, and it also includes 200 connectomes for each ensemble, which describe which neuron is connected to which. We did quite extensive pre-computation. This was done in Python in order to take advantage of Unity's status as a game engine. For example, we rendered the attributes into textures so that they can be loaded by Unity's texture system and be available in shaders for computation on the GPU. We also encode the connectomes as meshes, and this allows us to render them as simple game objects in Unity with a specialized shader, which then selects which connections are shown. Here we can see a screenshot from our application and an example expression that was entered. The expression is grad for gradient and map of the activity attribute from -70 to 30 millivolts to range from 0 to 1. So the -70 millivolts will be displayed as black and the 30 millivolt levels will be displayed as bright yellow. The UI allows us to skip around the selected frames and to replay it at 60 frames per second or lower. We can choose different gradients, and by right-clicking on the surface we can select a neuron and display its connections. The connections are organized by whether they are new in this frame, deleted in this frame, or persistent. And we can display any combination thereof. So for example, if we decide to show new and deleted connections, that would be the flux. Because we evaluate the expressions on the GPU, this is very, very efficient and runs in real time even on older hardware. Here we have another example. We use the RGB expression to show 3 channels at once. In the red channel we can see the fired attribute, where a neuron has just fired in the last frame, and the blue channel is the same activity expression from last slide. So we compare the electrical activity with whether the neuron has fired in the last frames. We can see that there is no magenta, and this is due to the refractory period, because after a neuron fires, the electrical potential falls to its lower point, and that would be represented as a color with little to no blue. And this doesn't overlap with the fired state, because the fired state needs a buildup of electrical activity. Of course, there are many other examples that could be realized. For example, we could take the difference between the total axons and the connected axons for each neuron and get a visualization of how many axons are available for each neuron. Overall, our approach is promising, and we have achieved our goals of creating an interactive real-time application. The use of preprocessing and the GPU allows the application to run performantly even on older hardware, and the expressions allow great flexibility for what to visualize, and we, the authors, have not explored this fully yet. The project was built with Unity, so it can be easily extended in the future and be built upon or used in other projects. Thank you for listening.